We've been keeping you updated on 3I Atlas and its strange behavior, and now another shocking update is on the way. A new signal has emerged that could change everything we thought we knew about this interstellar visitor and the unusual cosmic events surrounding it. Stay tuned as we go deeper into the latest discoveries and unravel the mysteries trailing this silent visitor through our solar system. NASA's Fermi Gamma Ray Space Telescope has detected an unprecedented burst of high-energy radiation, and here is the part that has scientists around the world losing sleep. This violent eruption of gamma rays came from the exact same region of sky where 3I Atlas first appeared. The burst, now officially labeled GRB 250702b, shattered every record in the history of gamma-ray astronomy. It lasted over 7 hours. 7 hours of continuous, pulsing, high-energy radiation streaming across 8 billion light-years of space. To put that in perspective, most gamma-ray bursts last a few seconds. Some stretch to a few minutes. Scientists have observed thousands of these cosmic explosions over the decades. None of them behaved like this one. The burst emerged from a dust-choked galaxy so far away that visible light could not escape. Only the highest energy radiation made it through, suggesting an extraordinarily narrow and focused jet traveling at over 99% the speed of light. That jet was aimed surprisingly close to the plane of our solar system. When researchers compared the sky coordinates, the timing, and the trajectory data, they found something that made their blood run cold. Two independent, extremely rare cosmic events were pointing toward the same neighborhood of the constellation Sagittarius. This is the same region of sky, by the way, that became famous for the 1977 WOW signal, that unexplained radio transmission that has puzzled scientists for nearly 50 years. Public statements from NASA and other space agencies have remained cautious. They emphasize that no physical link has been proven between the gamma-ray burst and 3I Atlas. The distance of 8 billion light-years seems to rule out any direct interaction. But in private conversations, astrophysicists admit that this alignment demands much deeper investigation. Statistically, the probability of such events converging in both time and space is extraordinarily low. Some researchers are calling it the most significant cosmic coincidence ever recorded. And this is just the latest development in a story that keeps getting stranger by the day. To understand why scientists are so concerned, we need to go back to the beginning and trace how this mystery unfolded. It started quietly, the way most universe-changing events do. On July 1, 2025, astronomers detected an unfamiliar object slipping into our solar system. It was not orbiting the Sun. It was not slowing down. Its path made one thing absolutely clear. This object did not belong here. Scientists gave it the name 3I Atlas, marking it as only the third confirmed interstellar visitor ever recorded by humanity. Think about that for a moment. In all of human history, with all of our telescopes and satellites and space probes, we have only ever confirmed 3 objects that came from another star system. The first was Oumuamua in 2017, that strange cigar-shaped object that sparked wild speculation about alien spacecraft. The second was Comet Borisov in 2019, which looked more like a traditional comet but still raised plenty of questions. And now we have 3I Atlas, and it might be the strangest of them all. Less than 24 hours after 3I Atlas was spotted, NASA's Fermi telescope registered that extraordinary gamma-ray burst we just discussed. The timing was remarkable. 2 incredibly rare events, occurring almost simultaneously, coming from the same direction in the sky. Scientists immediately began asking questions that had no easy answers. Was this pure coincidence? Was there some connection they were missing? Or were they looking at something that would force them to rewrite the textbooks? The public disclosure of these findings did not happen immediately. The full details were released only days before 3I Atlas was scheduled to make its closest approach to Earth. This delay fueled speculation and debate across both scientific communities and social media platforms around the world. Standing alone, none of these facts proved anything dangerous. But together, they formed something far more unsettling. A pattern. And just as astronomers turned every available instrument toward this silent visitor, its behavior began to reveal details that no one was prepared to explain. Once the initial shock faded, scientists did what they always do. They started measuring everything they could about this strange visitor. 3I Atlas was not just another object drifting through space. Its path told a clear story. It was moving too fast to be captured by the sun's gravity. Its trajectory was sharply curved, a signature of something born around another star and ejected long before our solar system ever noticed it. Telescopes across the world locked onto the object. Data poured in from optical, infrared, and ultraviolet instruments. At first, 3I Atlas appeared comet-like. It showed a faint coma, which is that fuzzy cloud of gas and dust that forms around a comet's core as sunlight warms its surface. That should have been reassuring. It was not. As 3I Atlas moved closer to the sun, its brightness began to change in ways that made no sense. Instead of steadily increasing as expected, the light fluctuated wildly. It brightened, dimmed, then brightened again without any clear link to distance or solar heating. Standard cometary physics simply could not explain what was happening. Then came the tail. Most comets develop tails that stream away from the sun, pushed outward by solar radiation and charged particles. 3I Atlas displayed something far stranger. Observers noted an anti-tail, a structure that appeared to point toward the sun rather than away from it. This phenomenon is rare but not impossible. What troubled researchers was how stable and persistent this anti-tail remained over weeks of observation. The rotation data added another layer of unease. Typical comets tumble irregularly, spinning faster or slower as jets of gas erupt from their surfaces. 3I Atlas rotated smoothly. Its spin rate remained controlled and consistent, showing none of the chaotic behavior scientists usually expect from a loosely bound icy body flying through space. Harvard astrophysicist Avi Loeb later stated publicly that the object exhibited at least 15 distinct anomalies. Not random quirks. Not measurement errors. These were persistent features that remained consistent across multiple observations from different telescopes around the world. Meanwhile, the gamma-ray burst itself raised more questions than answers. It originated nearly 8 billion light-years away, inside a dust-choked galaxy where visible light could not escape. Only infrared and high-energy radiation made it through, suggesting an incredibly narrow and powerful jet traveling at nearly the speed of light. That jet pointed in the general direction of our solar system. By this point, scientists were no longer just asking what kind of comet this was. They were asking whether it was a comet at all. Here is where things get really interesting. As 3I Atlas moved deeper into the inner solar system, space-based observatories began detecting something that nobody expected. The object was not just reflecting sunlight or releasing gas and dust. It was actively emitting high-energy radiation. X-rays. Now, X-ray emissions from comets are not completely unheard of. They can occur when solar wind particles slam into a comet's coma, creating a brief glow of radiation. Scientists have observed this phenomenon before and understand the basic physics behind it. But what they observed with 3I Atlas did not behave like any comet they had ever studied. The emissions were stronger than expected. Much stronger. They were also far more persistent than normal comet interactions would produce. And they appeared earlier in the object's approach than any model predicted they should. ESA's XMM Newton telescope confirmed the signal, marking the first clear X-ray detection ever associated with an interstellar object. That discovery alone made scientific history. But the details of those X-rays raised even more concerns. The emissions showed structure. They came in patterns. There was a rhythm to them that suggested stability rather than turbulence. This was not the messy, random interaction of solar wind hitting an irregular cloud of gas. It looked organized. Researchers attempted to explain the readings through known physics. They tested plasma interaction models. They adjusted solar wind density assumptions. They recalculated coma size and particle flow a dozen different ways. None of it fully fit the data. Even more troubling, the emissions appeared to fluctuate in cycles that did not match solar activity at all. They rose and fell independently, as if driven by something internal to the object rather than external forces from the sun. Then came another surprise. Water is common in comets. Ice warms as it approaches the sun, vapor escapes. Jets form. This process is well understood and has been observed countless times within our own solar system. When NASA's Swift Observatory detected hydroxyl signatures around 3I Atlas, scientists initially felt a sense of relief. This was familiar territory. That feeling did not last long. The amount and behavior of the water emissions did not match what the models predicted. The jets were not erupting randomly across the surface like they normally would. They appeared localized, concentrated, and they were repeating in patterns that suggested fixed release points rather than spontaneous cracking of the surface. Even more puzzling was the chemistry mixed into those jets. Carbon dioxide dominated the emissions, which is unusual because you would normally expect water to be the primary component at the distances 3I Atlas was traveling. Carbon monoxide and other volatile compounds also appeared in ratios that did not align with any known formation models. Scientists compared the data to every known class of comet. Long-period comets, short-period comets, even fragments from the distant Oort cloud. None of them provided a clean match. Then there was the temperature problem. Thermal imaging showed that parts of 3I Atlas were cooler than expected while still actively releasing gas. Other regions appeared warmer without showing any corresponding activity. The energy balance did not behave the way simple sublimation physics predicted it should. Its ultraviolet signature added another layer of confusion. Instead of showing a diffuse glow like normal comets, the emissions hinted at structured regions, almost compartmentalized. This implied internal organization rather than a loosely bound mixture of ice and dust. This was no longer just a discussion about chemistry or radiation levels. It had become a heated debate about interpretation, scientific caution, and the limits of what we can claim to know for certain. Inside scientific circles, opinions began to separate along clear lines. One group argued strongly for restraint. They pointed out that interstellar objects come from environments far our observational experience. Different stars mean different chemistry, different radiation histories, different formation processes. To them, 3I Atlas was unusual, certainly, but not impossible. The universe is vast and strange, and we should expect to encounter things that challenge our assumptions. Another group was far less comfortable with easy explanations. Avi Loeb became the most visible voice among those urging deeper scrutiny. He did not claim proof of anything extraordinary. Instead, he focused on the accumulation of evidence. 15 documented anomalies. Stable rotation. Structured outgassing. Persistent energy emissions. Survival through stress zones that should have torn a loose, icy object apart. His argument was elegantly simple. When too many independent anomalies stack together, dismissing them individually becomes a form of bias. This stance drew fierce criticism from some quarters. Researchers accused Loeb of inviting wild speculation. Others warned that public discussion could fuel dangerous misunderstanding. Please like and subscribe channel.